I would like to thank the organizers for inviting me here. I will talk today on the metastable behavior of spin S Ising and Blume-Capel ferromagnets. So this work has been done in collaboration with Momita Noshkar, Errol Bhatansevar, and Nicholas Fitas. And here is the reference of our publication. So what is metastability? Metastability is an intermediate energy state of the dynamical system other than its state of least energy. So here is an demonstration of metastable behavior observed in the spin half Ising system in contact with a heat bath. So if the initial condition of the system is all spins are up, here we have only two directions, up and down, for the spin half system. In this case, the magnetization is plotted against time, and the system remains in its metastable state over a long time, and then suddenly jumps to the stable state. And note that this is stable state of least energy, but these states, the energy of this state is higher, and this is the metastable lifetime. Okay, so how can we understand this metastability or the metastable behavior for spin half Ising system? So imagine that there is a formation of this kind of droplet of down spins in the sea of up spins, and the energy of formation of this droplet of size L is given by this formula. So this is the bulk energy, H is the applied magnetic field in the opposite direction, and this is the surface energy. And from this diagram, it is clear that there is a critical size of the droplet above which the supercritical droplet will always grow in size and the subcritical droplet will shrink in size. And in this way, the system escapes the metastable state. Actually, these supercritical droplets plays the active role in escaping the metastable state. So, how can we calculate the metastable lifetime? So this is the energy, this is the critical energy, basically the energy of the critical droplet, and number of critical droplet is given by this exponential formula. And this is the basic assumption of the classical theory of nucleation, that Baker and Doring theory, that the rate of increase of number of critical droplet is proportional to the number of critical droplet already present here. The metastable lifetime is given as the inversely proportional to this rate of creation of supercritical droplets. So there are two distinct regimes in this system. So for small values of the field, weaker field, a single supercritical droplet grows in size, and in relatively higher values of the field, the number of supercritical droplet forms, and they coalesce and forms the bigger droplet. And in this way, system escapes the metastable state. The question is, what will happen if the spin is not simple spin half, so that there are some intermediate projections of the spin values. The spin projection can take the values from -s to +s, total 2s plus 1 number of values. And this is the model Hamiltonian for general spin S Ising and Blume-Capel model. In Ising case, the anisotropy is 0. If put this single site anisotropy, this d equals to 0, this gives you a spin S Ising model, and for non-zero value of d, you have the spin S Blume-Capel model. And this is the Zeeman term, that external field is denoted as H. And we have performed the extensive Monte Carlo simulation with Metropolis single spin flip algorithm. Here is the expression of the probability of spin flip given by the Metropolis rate. And here is the result. It shows that the different color represents the different values of the spin. If you plot the magnetization versus time, you see that there is a metastable state, and this is for spin half, and this color is for spin 1. And from this picture, it is clear that metastability becomes short-lived as you increase the value of the spins. And this similar picture was also observed in the case of Blume-Capel ferromagnet for a constant value of the anisotropy. We have used the value of the anisotropy, which is equal to 0.5 here. And how can you calculate the metastable lifetime as a function of the applied magnetic field in d dimension? So this is from the classical nucleation theory, from Becker and Doring theory, that logarithm of the metastable lifetime is given by this formula in the multi droplet regime, where the droplets coalesce to form the bigger droplet. And in the single droplet regime or in the nucleation regime, the logarithm of this metastable lifetime is given by this formula. And note the difference here, there is an extra factor of d plus 1. So if one plot the logarithm of the metastable lifetime as a function of 1 over h in 2 dimension, so there will be a difference in the slopes. So now see the results of our Monte Carlo simulation, and we have plotted this logarithm. Actually, it is in the log scale. The metastable lifetime is plotted against 1 over h for different values of the spins, s equal to half, s equal to 2, s equal to 5 over 2, and s equal to 3 in the case of Ising model, general Ising model. So note that this is the clear nucleation regime where the single supercritical droplets grows and the slope is higher. And this is coalescence regime where the multiple supercritical droplets coalesce and system leaves the metastable state. And this is same for all values of the spin. And if we study this in Blume-Capel ferromagnet, where d is non-zero, we have the similar observation here. Here is the nucleation regime where a single supercritical droplet grows, and this is the multi droplet regime where they coalesce and form the single droplet to grow. Now the question is, how does the metastable volume fraction decay? As the system leaves the metastable state, the metastable volume fraction decay with time. Metastable volume fraction is defined for spin half Ising system as the relative abundance of up spins, and this follows the Abraham's law in d dimension. This is d plus 1. So we have studied in 2 dimensions, so that power will be 3. And here is the result. We have plotted this for Ising s equals to 7 by 2, and the logarithm of the metastable volume fraction is plotted as the cube of the time. And see that the long time behavior is a straight line, and this gives you the Abraham's law. And the similar observation made for the Blume-Capel ferromagnet. Here also we observe that the metastable volume fraction decay following the Abraham's law. So the conclusion is the Monte Carlo results of metastable lifetime of spin s Ising and Blume-Capel ferromagnet are in good agreement with the classical theory of nucleation, which was originally studied for spin half Ising system, spin up and spin down. And here we see that our spin s, general spin s model also obey these classical nucleation results. The Monte Carlo results of decay of metastable volume fraction are in good agreement with the Abraham's law. Thank you for your patience.
Hello.
Hello.
What are the results one can expect in the quantum version? I mean, is it similar?
I do not know. This is classical.
Yeah.
The system is interacting with the heat bath.
Yeah.
And we use the classical Monte Carlo.
Achha.
For quantum case, you have to study by using the quantum Monte Carlo.
Yeah. We have quantum cluster updates for that. One more question. I mean, you have taken the initial state to be ferromagnet, right?
Initial state is?
I mean, prepared the initial state in the ferromagnet.
All spins are up.
I mean, you have, like, for example, what happens when you have initial state in the critical region? I mean,
no, if you want to study the metastable behavior, you have to start with that kind of initial conditions where all spins are up and apply a field in the reverse direction. So that is the usual procedure.
Thanks.
Hi. high. So I probably missed it, but you said the higher spins having a lesser
In our case, it is 7/2.
like how do you understand that? Like higher spins having a lesser metastable lifetime.
Yes,
Uh,
that can be understood in this way. Suppose you have the spin half system. So if you have the spin half, in the metastable state, all the spins are up, and after applying the magnetic field, the stable state will be all the spins are down. So there is no intermediate projected states in that case.
I see.
But if you select the spin say 5/2, so your intermediate states will be 3/2 half, etc., etc. And the flexibility of the spin increases by increasing the S value.
Got it.
So that is
Thank
the
you.
reason.
Do you expect any deviation from the classical nucleation theory in the presence of disorder?
Even there is a deviation. You have noticed probably that this slope and that slope should be 3 times higher of that slope according to classical nucleation theory. But note that this is not actually 3 times higher. So there is already deviation there, but certainly if you incorporate the disorder, maybe dilution or say random field Ising model, we have already done so. Actually, the Momita did in her PhD thesis. In that case, we have found the deviation. If you increase the randomness, the width of the randomness of the random field, certainly you will not get the nucleation regime. And it is published in 2020.
If there is no question, let's thanks to the speaker.
Okay, thank you.